and we want to find the result. Like for each position, we will calculate the distinct elements in the prefix and also in the suffix, and the answer will be the distinct number count of prefix minus the distinct number count of suffix. So this is quite a direct solution that we just iterate this array from begin to end at first, and we use side to calculate distinct element count, and then we iterate it again from end to begin and calculate the distinct element count again, and then we construct the answer, use the prefix number minus suffix number. So that will construct the answer. This is the first problem. For the second problem, it means we may calculate the frequency. So for this problem, we will be provided a class with three methods. The first one is go to add a number, and the second method is delete a number, and the third method is ask a question. It's like we provide a frequency, and if any number that is existing frequency equals this frequency, then we provide we return true, otherwise we return false. So for this problem is also very direct solution. It's like we use two maps. For the first map, we calculate so the key will be the number, and the value will be the number's current frequency. And for the second map, is the key is the frequency, and then the value is this frequency's count for all of the numbers. So for add method, we will update its existing frequencies count by -1, and after we update the current number's frequency, we update the frequency again. So this is update the current frequency, and very similar for the delete. Like we will update the current frequency by -1, and then we update this number's frequency, and then we update the frequency count again. And then for this method, we just check whether this method is already exist in this map. If its value is bigger than 0, then we return true, otherwise we return false. So this is the second method. For the third problem, the problem is go to find the number of adjacent elements with the same color. So for this problem, it looks like we may provide n. So n means how many elements in the array. Like all of the array's initial color is 0, means no color. And then we will also provide another vector of named queries. For this vector, we will provide several elements, and for each element, it has 2 elements. The first element is the index, and the second element is color. Means we will paint the elements at this index with this color. And then for each paint, we need to calculate how many adjacent elements have the same color. For example, for the first example, like initially there is 4 elements with 0, and then we paint the first one with 2, and then now the answer is still 0, and then we paint the second one with 2, and now the answer should be 1, because we have 1 adjacent elements, they have same color. And for the third query, that we will paint these elements with 1, and now the answer is still 1. And next operation is we paint the second element with 1. And now there is no adjacent elements with same color, so the answer is 0. And for the last query, we paint these elements with 1. And now we have 2 adjacent elements has the same color, so the answer is 2. So for this problem, the key observation is when we color one element, the only impact to the answer is decided by the elements adjacent to it. Such like we paint this element, then we just need to check elements before it and elements after it. We just need to check these 2 elements and update the answer. So it looks like this. We iterate the query, and then we get the position and color from the query. And we may check whether the current elements at this position's color equals with the new color. If they are equal, then no update to the current answer. So we just assign current value to the elements in the result. Otherwise, means that we need to update this value. This value means how many adjacent elements have same color. And we will check whether before we make the change, whether it has same color with its previous elements. If it's true, then we minus this value, because after we make the change, the color must be changed, and it must be different with it. The color must be different with its previous element. So the value will be -1. And the same thing, that we will check the elements after these elements. If they were equal with about color, then we also minus the value. And then we update current elements with the color. And then we check again to see whether now they are equal. If they are equal, then we plus current value by 1. And similar things that we check the elements after current elements and update this value. And then we assign the current value to the elements in the result. This is for the third problem. And for the last problem, this problem make cost of paths equal in a binary tree. So we will provide a perfect binary tree. Means this binary tree, for each element, and so unless it is a leaf, otherwise each element has 2 child. And now for each node, there is also a cost, such like for this node, its cost is 1, this node's cost is 5. And the target is we want to guide the path from the root to any leaf. There, the sum of cost on this path equals, so for all of the leaves. And in order to achieve this goal, we can increase each node by 1. Like we can increase roots. We can also increase these nodes. So after we increase these nodes, all of the paths through these nodes will be impacted. And our answer would be what is the minimum operations that we can achieve the goal. That we update the nodes by 1. So this is one operation. And we can apply this operation on any of the nodes. And then we want to understand what is the minimum operations we need to make to achieve the goal, like all of the paths from root to leaf, they are the sum of the cost of the nodes on this path equal. So for this problem, let me try to draw something to explain this the solution for this problem. So for this problem, for example, that we have this perfect binary tree. For example, we have 4 layers. Okay, first of all, we need to calculate the sum of the cost on each pass for each leaf. So we need to calculate this pass cost. So let's say we call this C0, and this cost on this pass is C1, this is C2, this is C3, this is C4, this is C5, this is C6, this is C7. Okay, so we need to calculate this, and then we can think about the such like the because we need to get the minimum number of operations. So if we can update the nodes from on the upper layer, then we should do that. Just one example. For example, this cost is 1, and this cost is 2, this cost is 3, and for example, all of these costs are 4. So in this example, that we should update these nodes from 2 to 3 to achieve the goal that all of the leaves cost equal. But so we can also do this on these nodes. That we can also do take 2 operations that add this node's cost by 1 and also add this node's cost by 1. In that case, we can also achieve the goal. It's like this will become not 4, this will become 5. This also become 5, and this node is still 2. Then in this case, the array leaves cost is also same. But the problem is for this one we need 2 operations. So we shouldn't do this. We should still keep this at 4. And we should change these nodes. We should change this from 2 to 3. And we just need 1 operation to achieve this goal. So that means if we can change any node's cost at higher layer, then we should change that node other than change the nodes at lower layer. And then how do we know what is the cost we can increase for higher layer? So first of all, we need to calculate all of the cost at the lowest layer, at this layer at first. And then here we will get the maximum cost for among all of these leaves. So for example, this is the max cost we already have. So now the target goal is we want to change all of the other leaves cost equal with this max cost. And to change that, we need to calculate like how many costs I can add for them if they are under the same ancestor. So now here for the root nodes, definitely no need to update its cost because we update root cost. It's just update cost for each of the leaves cost equally. So we no need to change this node's cost. But for this one, like if we change this node's cost, it will impact the leaf on the left side. And when we can update this node's cost, until all of these nodes cost, they are lower than this max cost. For example, if max cost is 4, and for these 4 nodes, these 4 leaves cost, for example, there are 2, 3, 1, 2. And in this case, we can see that if we update this node's cost by +1, then these 4 nodes cost will become 3, 4, 2, 3. So we can see they are still not bigger than this max cost. So that means we can add this node's cost by 1. And now when we check that there is the maximum cost on the left side is 4. So that means we cannot update this node again, because if we update this nodes by cost by +1, then these nodes, the maximum, the cost of these nodes will change from 4 to 5. So it's bigger than the max cost of the original LeetCode. So we cannot change this again. And now we will go to the lower level. Like we will go to this level, and then we may check that for these two nodes, that is have the same ancestor of this node, and then we may check their maximum elements is 4, so equals with max cost. Then that means we cannot update this node's cost either. And if we check these nodes, we may check that the child of this nodes is only 2, 3. So that means we can add these nodes by +1. Then his child will become 3, 4 now. And the max cost of each child is still not bigger than max cost. So that means we can add these nodes by +1. So this is the general idea like how we should resolve this problem. And we can check that the key observation is we may get all of the cost, the original cost of all of the leaves, and then we will split them by left and right, and then we will check whether the left side cost they are smaller than the max cost. If they are smaller, that means we can update their ancestor by plus the diff of their max cost, and this the total max cost. So we can update their ancestor, and then we will split this side again from to left and side again and right side again, and then we will check their ancestor separately. So this is just like a recursive algorithm to resolve this problem. So let's see how we implement this. Okay, so first of all, we may calculate how many leaves we have. So this will be n plus 1 and divided by 2. This is the leaf cost of the perfect binary tree. And here we may have this cost. And then we will iterate from the first elements and update the first element's cost to all of its child. And finally, for this vector, the second half of this vector will be the leaf's cost of their path. And the next one, we may define a variable named the target. And this target will be, so here we will calculate what is the maximum cost of all of the current leaves. And this is the target we want to achieve, the final states. The final state. And here I write this method use a recursive algorithm. So for this method, it have the vector of cost, and also it has the right position and the left position and the right position of the elements that I want to process in the current method call. And the target is the final target is the max cost of all of the leaves, and added means how many costs I already achieved. The added cost I already achieved by the ancestor at higher layer. And now what I want to do is I want to calculate the current maximum elements in the range from left to right, and this answer means how many costs I will, how many operations I will make in this at the current layer, and also at the layer of the below it. And here first of all, I calculate how many operations I may make based on the current maximum elements in all of the elements I want to process in the current call. So this will be the final target minus current elements max cost, and also minus the added cost I already achieved from the higher ancestor. And so I update this value to the answer. And now I check whether this is there is still some elements I want to process. If it is true, then I will divide the current range to another left side and right side, and then call this method again to calculate any cost at a lower layer, and then also added the result to the current variable for the operations, and then return this operation. Okay, so this is just use a recursive algorithm to resolve this problem. Okay, so this is all of the solutions for the LeetCode's weekly contest 344. If you have any questions, let me know. Thank you.